Alright, welcome back to our little tutorial. For this module we will do it in 3 parts, similar to your assignment, one jet performance part, one prop performance part and one landing performance part. Let's start first with the jet performance part because it's the most straightforward from what we've done so far, and then head into prop and landing performance afterwards. From what we've done so far, before the midterm, we finished off with the discussion of drag and basically developed a total drag curve for our aircraft, for our example aircraft. And that total drag curve is basically again shown here on the left side in that first diagram. And we noticed that the drag curve itself has basically 3 main parts. It has a side on the slow speed side, which has a lot of drag, and the slower we go, the more drag is basically applicable on that side, mainly due to a large part of induced drag on the slow speed side and a small part of parasite drag on that side. Then it goes into a minimum at a certain speed, which is basically the intersection point of parasite and induced drag, and from there it increases then on the other side again to the faster speed, and now the main influence here is the parasite drag, and the induced drag becomes less and less a factor in our total drag curve. So that's the general drag curve. One more point to point out here is to the far left, stall, which is basically the limiting factor here, and again the min point. Those are the 2 big points, or the 2 main points in that curve that were interesting so far. And then at the high speed side we would also start seeing compressibility effects and wave drag as we get towards supersonic flight here, but that's not too much of an issue or too much of a concern for our discussion here in performance right now. So the general drag curve basically being what we are seeing here. The main one big point to keep in mind with all those curves we're talking about here, and because we are starting with the drag curve, each drag curve is obviously very specific to the aircraft that we are looking at. Each aircraft will have a different drag curve based on design features like wingspan, wing area, taper ratio, aspect ratio, wing sweep, which goes all into the efficiency factor, which influenced basically how much drag we will see on each of those sides. So the curve in general will always look somewhere like stall, then a decrease down to a minima, and then increase again as speed goes up, but the exact points, which speed we are looking at and how stretched or how flat that curve looks, will be different from aircraft to aircraft. So the first main point here for all the performance discussion is that we're always looking at the right curve for the right aircraft that we're interested in. So make sure for the assignment that you're looking at the figure that was given in the assignment and not any other figure in the book, because it is not interchangeable. So each figure is for one specific aircraft at one specific gross weight most of the time, at one specific altitude, and so on. So make sure that you're in the correct figure, because as I said, each drag curve is different for each aircraft. They are not interchangeable. Alright, from the drag curve, how do we get to the performance thing? The big assumption, again, in all our discussion so far, until we get into accelerated flight, into turning flight in one of the next modules, everything we discussed so far is basically equilibrium of forces, which means, as we know, that lift should be offsetting drag, weight. So lift should equal weight for all our flying, but then also our drag that we have on the aircraft has to be offset by some sort of thrust in the opposite direction. And this equilibrium here, down here in the corner that I just mentioned again, is the overarching theme and the driving factor in all our performance discussion. So what we basically have with the lift, with the drag curve here, is a direct result of the drag that is on the aircraft is how much thrust we need to overcome that drag. So how much of this thrust will be required to overcome the drag. And that's really why that drag curve directly becomes also our thrust required curve, as we can see here in the next diagram. So every time we talk performance, the basic drag curve that we developed over the last module before the midterm is the exact same curve that will be our thrust required curve in all our discussion for performance. So it tells us basically how much thrust the aircraft has to develop to achieve that equilibrium of forces for flight, and that goes for any flight that is not accelerated, so any straight and level flight at one altitude, but also climbing and descending flight, as long as we don't have acceleration, so as long as we don't have any circular flight paths involved. If you're going in a straight line up or down in a climb or in a descent, we still have an equilibrium of forces, and we will see how that affects us, or from the book reading you should know already how that affects us, especially when we're talking about climb angle here in a little bit through the assignment. So again, bottom line is that our drag curve becomes, for our performance discussion, our thrust required curve. It is the same curve with the same features. It has a stall on the left, minimum point in the middle, and then increasing thrust required as speed goes up. And based on that, we also have a minimum point where the thrust required will be at the minimum, which is the same point as the minimum drag point, or L over D max point. All those are interchangeable for the performance discussion, because we've seen now from our drag discussion that minimum drag, as we discussed it before, minimum drag down here is the same as L over D max, or the maximum lift we can get per drag, which is the same as the minimum thrust required in this curve, and it is the minimum point of the drag curve or of the thrust required curve. And since it is a minimum, you can easily find it by taking a ruler, putting it straight across your table, basically in a straight horizontal line, and then moving it up till you start intercepting. Need a little paint here. Start moving that ruler up, always keeping it horizontally straight till you start intercepting the curve at one point. So when your straight horizontal line becomes a tangent on your curve, then you're at the minimum thrust required curve, or at the minimum point of that curve here. And then you can directly read associated speeds and thrust required values, in this case in thousands of pounds of thrust here on the left, and the associated speed on the bottom. Again, same things as we talked about before apply. When you look at the diagram, take a first look at what is it, what two values is it relating to each other, in this case speed and thrust required, and in which units are we talking about those things, and which units are we talking about those things. And it even tells you here, in this case the thrust required would be 830 pounds based on this diagram, because it's the minimum point down there. One note here also to the diagram reading, you see those cross-hatched area. That's not actually cross-hatched, that's little millimeter squares, and they help you assessing basically in a more detailed way what the actual minimum is when reading that curve. So you don't actually even need the ruler, you can just look at those little squares and start counting squares from the bottom up to the minimum point here, and you should come out with about 8.5 of those squares, but that's why it ends up to be 830 pounds here for 8.5 of those little squares on the bottom there. And you can also directly see all the areas that are interesting have basically those cross-hatched areas here, or those little millimeter squares. So those should help you in assessing the exact points on those curves when you're working your problems, your performance problems for this week's assignment. One last note on generally working the assignment this week. All the assignments will be a combination of calculation of formula work and graphical solution. So you will need both. You need input values from your charts, and then you have to use those values within your formula. So as we talked before, for chart reading or for the combination of where do variables come from and how do we put them into the formula, all those good points apply as well in this module here. Alright, having said all that, let's get into the specifics. We already covered a little bit where to find minimum points on the curve, and we will see how we will need that in just a second here. So we said the drag curve is basically becoming the thrust required curve for all our discussion in performance. Then the second part that goes into performance is obviously how good is my aircraft in doing thrust, and that's the thrust available part. And as we can see in that third curve here, the thrust available part can be directly overlaid in the same diagram as a curve, which helps us finding graphical solutions and telling us basically directly the relationship between thrust available and thrust required. Why is thrust available important? First off, obviously if we have less thrust available than thrust required, then we can't fly under those conditions, which basically means we exceeded the performance capabilities of our aircraft in that case. Where do we see that normally happening? If we're flying too fast, because then we start getting values obviously here on the right side of the curve that are beyond what we are capable of producing. And where do we also see it if we're flying too high in altitude, because our engine performance goes down, so the thrust available curve will move downwards as we are going up in altitude, and that again has the same effect that there's more of our thrust required curve that will be on the right side or above the thrust available line and will not be usable. So again, directly just from looking at the curve we can see that speeds above this here are probably not flyable, because we would need more thrust than we have available even at 100% RPM in this case, which directly gives us also the first performance criteria, which is the maximum speed that we can fly under the given conditions, which is the intercept point of your thrust available and your thrust required curve. It directly tells you from that intercept point what the maximum speed at that altitude would be. Again, just from looking at the curve, because anything that we fly faster, we have too much drag, which means we would need more thrust than we have available, which makes it impossible to fly there. So anything from here on is too fast flying for this type of aircraft under those given conditions, which directly makes this the max speed in this diagram. Alright. Now, talking about the assignment, first thing there is finding the climb angle. And from your discussion in the book, you should notice that the climb angle itself, based on how the vectors lay out once we start climbing our aircraft, part of our weight becomes actually drag. So this is part of the weight in our diagram that becomes drag, plus the natural drag that we have on the aircraft. So the thrust now has to overcome basically two parts here, which is, one is the part of the weight and the other one is the real drag part, and we need to overcome both with those in our thrust. So the thrust required becomes basically more based on geometry and how the angles or the climb angles work here, and therefore the climb angle relationship and also the maximum climb angle will be fairly dependent on how much thrust I have more available than how much thrust I would need under normal conditions, because that more thrust is basically what allows me to tilt the lift vector, tilt the weight vector in that case too, and add additional drag or add additional part of the weight vector onto my thrust required curve here. So how do I determine the difference between thrust available and thrust required? Just looking at the numbers here, at any given speed I can just go straight up from, let's say, 160 knots or whatever it is here, and find the two intercept points and build the difference between those 2 points. So the difference between here and here would be my excess thrust at 160 knots, if that was my 160 knot point here. So just by going from my 160 knot point straight up, finding the intercept point with my thrust required curve, and finding the intercept point with my thrust available curve gives me also directly the excess thrust that I have available. And as you can see in our climb angle formula, that excess thrust available minus thrust required, is basically what we will need in here to solve for the climb angle. Again, watch out, the climb angle, or the formula itself, gives you the sign of the climb angle, so you will have to build the arcus sinus of the climb angle, or arcus sinus of the excess thrust divided by weight, to get the actual angle there. So the actual climb angle will be the arcus sinus of thrust available minus thrust required divided by weight. Just to finish that thought here. And that's fairly straightforward, and again, all you have to do is find the right speed, find the thrust available at that speed, find the thrust required from your drag curve or from your thrust required curve, and build the difference between the two. Notice also that for jet, for most of our jet considerations, or for all of our jet considerations here, our thrust available curve itself, or our thrust available, doesn't change with speed. It will change with altitude, but it doesn't change with speed. It will change also with power setting, as you can see. So pay close attention which curve to use. This one is obviously not at 100% RPM. Use the one at 100% RPM if it asks for that. So it changes with power setting, obviously. That's why we have power settings, to use different power outcomes and thrust outcomes. And it changes with altitude, but in general the thrust available from our engines doesn't change much with speed. That's why you can see here basically a constant line. Constant, always anything that's horizontal in the diagram is a constant relationship, as we know from math. So you see a constant line here for the thrust available. So the real big thing here is basically the thrust required. The thrust available number in here shouldn't change much. So this number here, oh, wrong pencil. This thrust available number in here shouldn't change much in the formula and should stay at the same level where it was before, unless we change altitude or power setting in this case here. It also directly tells us if we have a constant thrust available and the variable thrust required, then the biggest excess thrust, and therefore the biggest climb angle, we can achieve whenever we manage to get the furthest distance between the two curves. Since one is a horizontal line, the other one will be the main dictating factor here, and that directly tells us that wherever the thrust required is at the minimum, we will automatically also have the maximum excess thrust for our climb. So wherever the thrust, the minimum thrust required is also our maximum excess thrust and our highest possible climb angle, if, for example, the final exam asks for something like that. And we know from our drag discussion that this minimum point, where the thrust required is minimum, is also our L over D max point, because again, the thrust required curve was nothing else than our drag curve, and in our drag curve the minimum point is also the L over D max point. So we directly can see a couple of relationships here between the thrust available and thrust required curve, and apply it to any climb angle at any speed, but also the maximum climb angle that is possible with that aircraft and the speed that it is associated with, which is the L over D max speed in this case. Alright, Good. That's all that there is to the climb angle. For the rate of climb, realize the formula is here. Put it down here. Realize there are 3 different formulas. The last one is the one we will be most concerned with, which is basically using the speed in knots, and the result will be in feet per minute. Notice also, again, it is dependent on the relationship between thrust available and thrust required. So the work in your diagram doesn't change. Just pay close attention what speed is asked for, and for which to build that thrust available versus thrust required, or thrust available minus thrust required difference. But how to build the difference didn't change from your climb angle example. You will still go in at some speed here. Let's take another color here. Let's take this color. If, for example, the question is at 400 knots, you would go in at 400 knots, go up to your thrust required curve, and then further up to your thrust available curve, and then build the difference between the thrust required and thrust available. And that's basically what would go in here, or goes in here for that speed. So it is, again, speed specific. And then that same speed that you used here, or that you found here, or that went in here, also has to go in here. And again, that makes the big difference. This part here, that you have the speed in there, makes the big difference between the angle and the rate of climb, and why there is a huge difference. If you now were trying to find the maximum rate of climb, it's not as straightforward as it was for the climb angle, because that speed would go in here. So in general, it has to be a higher speed than your maximum climb angle, similar to how endurance and range will be different from each other. One way how you would be able to get to the maximum climb rate would be how the book describes it, basically building a couple of those differences, building a curve form and finding the maximum of that curve. Another example is, or another way of doing it is converting your thrust available and thrust required curves for the jet also into power available and power required curves, because while the climb angle is dependent on excess thrust, the climb rate is dependent on excess power. Quick side note on that, the book is fairly consistent and fairly stringent with using only thrust discussions in the jet and only only power discussions in the prop area, which is fine, and which is one way of doing it. It has some advantages and it has some disadvantages. One of the disadvantages is that, as we see here, the rate of climb problem, the maximum rate of climb problem wouldn't be easily solvable. But again, you are not asked for that in your assignment anyways. I just want to mention it here, because the rate of climb is dependent on excess power, and we don't have excess power easily available from the thrust curves. So there is some advantage and also some disadvantage to doing it that way. However, we will stick with what the book is doing to keep it consistent with what you're reading there. Realize that in general you can transfer any thrust into any power required curve and any thrust available into any power available curve, with that basic relationship that we will look at when we get to the prop performance, basically by multiplying the whole thing by speed again, which is basically the big difference. So things to take out here for us are, or the big thing to take out here for us is, overall you should be aware that there is a difference between thrust and power, physically a difference and also numerically a difference when you work your examples. So pay close attention which curve you are in, what it is giving you, whether it's giving you thrust or power. In general, in the book, anything jet will be thrust, anything prop will be power, which makes it consistent for you for most work. So just keep that again in mind when you work him. Realize also at the other hand, on the other hand, that you don't have to stick in thrust only curves for jet and prop only curves, power only curves for prop. It is just one way of doing it. Just be aware when you're comparing and using things that you might have to convert one curve into another. If you're leaving those nice separation the book is basically doing there and keeping it nicely and separated. If you leave that that nice division between the two, then you're on your own and having to refigure your curves. Basically, that's what I'm trying to tell you here. So, in general, keep paying attention of what you're looking at. Is it a thrust? Is it a power curve? And keep attention to those little notes in the book and what they're trying to tell you. So keep in mind there's a difference between power and thrust. That's not the same, even though we in common language and in day-to-day use might use it interchangeably, but it is physically not interchangeably. There's a difference between the two. All right. Last but not least, no, not last but not least, two more we've got. We already talked about the max level airspeed and how to find that earlier. So the last two things that I've got here is max range and max endurance airspeeds. And for those two, the important part here is again thrust available versus thrust required. And the other part that goes in with those two is the relationship between fuel flow and thrust. In general, for the jet, we will assume that thrust is directly also related to fuel flow, which is fairly accurate actually from practical experience. So if you ever work with flying jet type engines, one of the techniques to set precise power settings is actually setting fuel flow. I flew a lot with fuel flow in Tornadoes and T-38s because it was a very precise method of setting a certain thrust output that you wanted to have. So thrust here on the left side, the thrust numbers here on the left side in general are also directly proportionate to fuel flow. So the more thrust you get out there, the more fuel flow you have to put in, which directly also tells us one thing. If we want to fly max endurance, then we want to minimize our fuel flow. Minimizing fuel flow means we want to get as low as possible on our fuel flow scale, or since we said it is equivalent to the thrust scale, we want to minimize basically the thrust required so that we can only put that little bit of thrust in, which basically means that we only have to put that little bit of fuel flow in. Therefore, the maximum endurance can be found by minimizing fuel flow, by minimizing thrust. So what did we know so far from minimizing thrust? The minimum we have in the thrust required curve is basically again our minimum point down here, and we directly also have a value here in case we want to calculate anything with it, but it is the same speed as before. It's the same L over D max speed that we talked about before, because it comes from the same thrust required curve, from the same, which is the same as the drag curve. So this, the minimum drag point, is also the minimum thrust required curve, which basically means if I don't need a whole lot of thrust, I also don't have a whole lot of fuel flow. So for anything endurance, we want to suppress the fuel flow as much as possible, keep it as low as possible. So the minimum drag point is also our best endurance speed point for all practical purposes, and again it has the speed associated on the bottom. For maximum range, it's not as easy, similar to what we've seen with the climb angle and the rate of climb. Yes, we can minimize the fuel flow, but since the speed gets fairly low, we are not making a lot of distance with that fuel flow. So in general, our speed for max range will be higher than our max endurance airspeed, because we try to make more distance with a fairly acceptable fuel flow. So in general, we can accept a slightly higher fuel flow if it gives us a lot of change in velocity, and so it must be somewhere in this bottom part here of the curve, and it must be to the right side of where we're talking, and it gets pretty crowded here in our picture. I will erase some of the stuff here in a second, but in general we can expect it to be higher than our max endurance speed, and we can expect it here somewhere in the less curvy part of the curve down here on the bottom. To find it exactly, to go back with the book method of doing it, let me erase some of this stuff here. Actually, let me just drag some of the stuff out here. Gives me some space to work with. Alright, in general, when we're looking at the diagram, so the maximum range is obviously dependent on velocity, we said, which is also part of the bottom of the curve here, because the faster we fly, the more distance we make. So what we're really looking at is exactly what it says here at the formula. Our maximum